Adjacency once I give him the microphone.
Okay, so is that working? You can all hear me? Hope so. Is that okay? Microphone's on? Yep, great. Okay, so I would like to tell you something about a subject very closely related to the previous talk, which is the appearance of cluster algebras in scattering amplitudes for gauge theories, in particular, this very nice toy model that some physicists enjoy playing about with because it reveals some of these structures in a nice controlled way, which is planar n equals 4 super Yang-Mills theory. And we heard many of the relevant points relating cluster algebras to scattering amplitudes in the previous talk, in particular that the scattering amplitudes are functions on a Grassmannian space. And in this theory, the relevant space is GR4n. So if we have an n-point scattering amplitude, the space that we're interested in, the kinematic space, or the space of energies and momenta of the scattering amplitude, is described by GR4n. And then the interesting questions come about, so precisely which function, what kinds of functions are these scattering amplitudes on this space? And they have interesting branch cut singularities at certain loci. And the question is, where are these branch cut singularities? What's describing them? And as Anastasia described in the previous talk, the cluster algebras have a lot to say about the structures of these functions. So what I'd like to do in this talk is sort of based on what she's told us in the previous talk, is to sort of connect a few things relevant in this story. So one is the notion of something called cluster adjacency. So cluster adjacency is a property about consecutive discontinuities of scattering amplitudes. So we know they've got all these singularities, they have branch cuts there. Suppose I analytically continue around one of these branch cuts and I study the difference of the function that I got from the function that I started with. I call that a discontinuity. What kind of analytic function is that, this discontinuity? And it turns out that the sets of singularities that you have access to after continuing around one singularity is not the full set of singularities. It's a restricted set of singularities. Okay, and that restriction is also encoded in the structure of the cluster algebra. So that's what we call cluster adjacency. And then I'm going to try and connect that to two other things, which themselves are very much connected. One is tropical geometry. So the idea that some of this cluster structure is already there hiding inside the tropical Grassmannian. And then something related to that is that we can study the space of Gröbner bases for the Plücker ideal describing that Grassmannian. And that gives us a Gröbner fan structure. And we can ask about, so inside there we'll find the tropical fan. And we can ask what data does this space of Gröbner fans, Gröbner cones, or the Gröbner fan contain relevant for the scattering amplitudes. And we're going to see emerging from it, again, the same set of singularities and the rules for adjacency, saying which singularities can go next to each other. So much of the combinatorial structure of the cluster algebra is already present, let's say, in the Gröbner fan structure for the original Grassmannian Plücker ideal. So I'm going to sort of try and link those points in this talk. There's a few references that are relevant. Let me point out there's also relevant to this is a paper, not by us, but by Bossinger, Mohammadi, and Nahera Chavez from last year. And I think Lara Bossinger is also going to give a talk at this workshop on Wednesday. And I don't know what she's going to talk about. She might be talking about the mathematics that's relevant to this discussion about singularities and amplitudes. Okay, good. So let me just remind you something that Anastasia already told you about. So we're going to work on the space GR4n. And why it's GR4n I'm going to skip, but I'm happy to discuss that more afterwards. But let's just take this space. And amplitudes are functions on this space. And they're also functions of one other parameter. So n in GR4n tells me the number of external legs of the scattering amplitude. They're functions on GR4n, and they also have one other parameter called the Toft coupling in the gauge theory. And we're in a planar gauge theory, and we're talking about perturbation theory. We're working in a weak coupling expansion for these scattering amplitudes. So there will be what's called a tree level contribution. And then at order lambda, there will be a one loop contribution. And order lambda squared, we have a two loop contribution, and so on and so on. So those were the loops that Anastasia was drawing in pictures on in the previous talk. And if we take the coefficient to L loops, then this is just, the coefficient function is just a function on GR4n. So this is the L loop amplitude. And it's a function on GR4n. Okay, now what kinds of functions are these? So at least for low n and L, so what functions? So if I take low multiplicity and low loop order, where we have data, the relevant functions are polylogarithmic. Okay, so they're polylogs of weight 2L. Okay, so let me just remind you what a polylog of weight 2L or polylog of some weight is. We have some function, we give it a weight k, and then to be a polylog, we should say that its total derivative is a sum over functions of weight k minus 1, one weight lower, indexed by some finite set of rational or perhaps algebraic functions of our kinematic data. So these A's here are rational or kinematic function, algebraic functions on GR4n. And I've got some finite set of those. And then when I take the derivative, I get a bunch of d logs of those functions spat out. Okay, and then I lower the weight by 1. So these A's sit in some set S, I'll just call S, but it's a finite set of letters that we call these. So these are the letters that Anastasia was referring to. Okay, now, so this class of functions comprises logs and dilogs and trilogs and so on, but of many variables potentially. Okay, now one useful thing that's helpful to characterize these functions is I can just, following this equation, I can keep iterating the derivative. And in each coefficient, taking its derivative and recording which letters get spat out when I do the derivative. So by following this equation, I can just iteratively define the symbol. So I take the symbol of the function f, and then I take the symbol of this thing. And here I will record just the argument of d log for brevity. So I'll put a tensor product and just record the letter A. Okay, and then I just keep applying that same definition recursively, and I will end up with a sum over a k-fold tensor product, so some vector in this A space of A's of length k with some coefficients, CA, and then the word A1 tensor, A2 tensor, all the way up to AK. Okay, so that's just something that records lots of information about the original function f that I started with. Okay, and in particular, notice that I get a bunch of words out and they're ordered, right? So if I take a derivative of this, that's acting just here on the last one. Okay, so that's the symbol. Right, so now I'm just going to recap something that Anastasia showed you. And since she already showed you, I don't feel bad about showing you my pre-prepared picture. So this is the same picture that Anastasia gave you on the transparency before. I draw the initial quiver for the cluster algebra associated to GR48. Or I could have kept going. I just keep adding more columns on the right if I want to increase the number of particles. And I picked 8 just to give an example, because we can say lots of things up to 8 or even 9, but at some point we start to run out of the things that we're able to say very easily. And then on the right here, I've drawn a picture of not this, but imagine I draw boxes, so I freeze nodes. So if I draw boxes on everything here except for this first column, that would be GR46. Okay, so GR46 is dual to a GR26. It's a 3-dimensional space. It has 3 active nodes in each quiver that I can mutate. The quiver that I would get by freezing everything here would correspond to this corner up here on this polytope picture. So that would be the initial quiver. Then mutating on a node, obviously I go away from one face and I go to a new face along one of these edges of this polytope picture. Okay, and to each face then is associated an active node of the cluster algebra, and therefore a cluster variable. And those cluster variables are the A's that I wrote up here in this 6-point scattering amplitudes. Okay, so this set S, sorry, is again for low n and L is the set of cluster variables. And that includes frozen ones. However, the amplitude should be homogeneous. So actually, I can always make, let's say in the 6-point case, I've got 9 mutable cluster variables corresponding to the 9 faces of here, and 6 frozen, which are in every quiver. So that's 15. But there are 9 homogeneous ratios that you can make out of those. Those would be the 9 letters in this set of cluster variables. Okay, or equivalently, I could say there's 15 letters, but many relations in these coefficients to ensure that the resulting function is homogeneous. Okay, so the new property, the property that Anastasia didn't discuss last time, is if I look at the symbol up there, the symbol of a given function is given by a sum over some coefficients, let's say they're rational numbers, with this k-tuples of letters. And the fact is you cannot have certain letters next to other letters. And the letters that are forbidden to be neighbors, are letters that correspond to boundary faces with no intersection on this polytope. So for example, so this is what's called cluster adjacency. So the singularities of the scattering amplitudes, not only is the set given by the set of cluster variables, but certain combinations are forbidden. So an example would be, let's see, what's forbidden? So this square, let's say, is 1, 2, 4, 5. And then next to it, I cannot put 2, 3, 5, 6. So those 2 square faces will never show up adjacent to each other in the symbol of one of these scattering amplitudes. Okay, so the absence of that pair is saying something about consecutive discontinuities of the function. I take a bunch of discontinuities until I reach this logarithm here, and I go around its branch cut. And then on the next sheet, I can't see this singularity. That's forbidden. Okay, so this is forbidden. And more generally, so also forbidden would be, let's say, this pentagon here, which would be at the back to 1, 3, 4, 5, can't also go next to 2, 3, 5, 6. So that's also forbidden. Okay, so that's a way. Oh, another way to state that is that you can only have two letters next to each other if you can find some cluster somewhere where they're both cluster variables. They're in the same cluster diagram. Okay, so I've drawn it for GR46, which is the last one I can draw, but it's also true for GR47. There you have the case with the 833 clusters and an E6 polytope, which I can't draw. But again, the same property holds, that you find that the scattering amplitudes, they have access to all 49 cluster variables or 42 homogeneous combinations of them, but you cannot have variables corresponding to faces with no intersection on the boundary of the polytope next to each other in this ordered word of singularities. Okay. Yes. Yes. Oh, sorry, SLN. You don't mean the SL4. Yeah, okay. Then, which numbers do you mean? Sorry. Yes, counting. I'm just counting the number of different cluster variables that you get in the cluster algebra. Sorry, yeah. So the question is, how does the set of cluster variables transform under the action of SLN? I don't know. I'll have to think about that. So one thing is that they preserve the cyclic structure. So it's not completely obvious to me that if I do a general SLN transformation, I'm going to take something that has a given cyclic ordering and end up with something with that ordering. So it hadn't occurred to me to think about representations of SLN for that reason. So, yeah. Yes. Okay, yes, that's true. So those are the minors, right? So you have all the minors in both 4.6 and 4.7, and in 4.6 it's only the minors, and in 4.7 you have these quadratics, but those quadratics come with a cyclic structure. So if I do a random SLN transformation, I think I'll get something outside the ordered set. So I'm not sure that I want to consider the SLN action on those objects, but I could be wrong, and I've not thought about it. So, okay, good. All right. So, oh, one other maybe comment to make, which is just a physical word in case you've heard of it, that these consecutive rules on consecutive discontinuities include something called Steinmann relations, which is something that's been known in the study of scattering amplitudes for a very long time in the physics literature. Okay, so that's just a word. Now, so what I want to do is to recover this structure without the cluster algebra, really. I just want to study the Gröbner fan for, well, GR4n, or more generally, I guess I can do GRKn, starting from just the Plücker relations for the Grassmannian. So obviously the minors of our matrix, let me stick with 4, n for now, obey some relations that you get by simply the fact that you can't anti-symmetrize on more columns than you've got space to anti-symmetrize on. Okay, so if I try and do a 5-fold anti-symmetric anti-symmetrization on these things that can only take 4 values, I'm going to get a 0. So I get some quadratic relations. Okay, so these are the Plücker relations. And so what we would like to do, instead of thinking about minors of a matrix, we would just like to study the space by defining it through the solution of these polynomial equations. So we can just replace our minors, just a meaningless equation, but it's meant to signify a change in notation, that I'm thinking about this as some fundamental variable which obeys the equations above. Okay. And then what I would like to do is study the space of Gröbner bases for this ideal. Okay, and there are many Gröbner bases for a given ideal, and they're comprised, or you can think of them as being each associated to a maximal cone inside some big fan. Okay, so this is going to give us a Gröbner fan. So what do? You pick some real set of some vector of real parameters. Let me call itWijkl for the weights that I'm going to rescale each of these Plückers by. And then I take all these polynomials and I rescale the Plücker Ijkl by some variable t to the power of the weight, Wijkl. And then what I can do is I can study the leading terms in each polynomial as I take t to 0. Okay, so that will give me a kind of the leading term, the leading form for each polynomial. And if I take the leading terms, as t goes to 0, I get what's called the initial ideal of the original ideal, indexed by my vector of weights that I've picked. Okay, so this gives me something called the initial ideal indexed by the weight vector W of the original ideal I, which is this Plücker ideal up here. And then I get a different initial ideal, and to each initial ideal is associated a Gröbner basis. Okay, so these are okay. Well, actually, I've mentioned Gröbner basis in the talk. What I really want is this initial ideal. This is the thing that's going to encode the combinatorics of the cluster algebra, as well as this rule about which neighbors are allowed, which letters are allowed to be neighbors and which are not. Okay. Okay, so I'm hesitant to do this, but let me do a simpler example just to sketch what you can get out of this. I'm going to do GR25, which is not one of my examples, but it contains all the same features as the examples that I do want to talk about, except for one complication, which I can mention at the end. So let me just write down the Plücker relations, or at least one of them. So I have a Plücker relation like this for GR25. Let me write one more. Okay, and then there's three more after this. Okay, so to study this fan of different possible Gröbner bases or different initial ideals, what I need to study is the space of weight vectors such that when I move a bit, I'm going to jump from one region where I get a given initial ideal to another one. They're being separated by walls in this weight space. Okay, so to do that, what's happening is that, say, two terms in this polynomial are being given equal weight on the junction between those two regions. Okay, so if I look at the Gröbner fan, what I'm going to find is the weight, let's say, for W, if it's this term and this term, the weight W12 plus W34 will be equal to the weight for this term. So that's one possibility. W12 plus W34 equals W13 plus W24. And they're both less than or equal to, because it's the leading term, the weight for this one. Okay, so that's one possibility of finding a junction between two Gröbner cones. Okay, but there's two other possibilities from the same equation. I could pick this term and this term, or this term and this term. So I've got various possibilities. Let me not write them, but there are three choices for each polynomial. And then for the next polynomial, similarly, three choices that I can write down, and for all five. So in some sense, I've got a space of 15 possible things that could happen. And the Gröbner cone is just defined by just the space of weight vectors where one of these 15 things happens. Okay, and if I go to that, if I put my weight vector equal to one of the satisfying one of these 15 relations, I will be on a junction between two cones. Okay, and this is related to the tropical space simply by replacing the ors that I would get down the left-hand side. Let me replace those with ands. If I replace those with ands, that defines for me a subspace of this Gröbner fan, which is the tropical Grassmannian. Okay, so and is for the tropical Grassmannian. And then you can study the fan that you get and I'm conscious that I'm running out of time. But I'm going to try and sketch this. It's the last example of a Gröbner fan that I think I can sketch. So, tropical Grassmannian has the structure of a Peterson graph, and it has 10 rays, which are these vertices. And it is a subfan of the Gröbner fan, which has 20 rays. So it has another copy of this, first of all. So here's 10 more rays, which are not in the tropical fan, but are in the Gröbner fan. And then the red rays are edges that are in the tropical fan. And the white edges are edges that are in the Gröbner fan. And I haven't drawn all the white edges because, for example, I would have to complete this graph with the edges that are missing in red. I have to put in all the edges in white. Okay, I'm not going to draw them because it will make a mess, but I have edges between red nodes, which are not edges of the tropical fan, but edges in this Gröbner fan. Okay, so I need to add, for example, edges here. And then if I label these things can have some labels corresponding to which pluka they go with. Then I'm going to get some edges that connect the two pieces as well. So there's some extra rays that I think, in fact, in this case, are just the negatives of the rays that you get in the tropical fan. And then these things will connect to things that they share one index with. So, for example, that would be one connection between the two pieces of this fan. Okay, I've only drawn an example of these rays and these edges and these edges. That's an example. Okay, so what's the point of this diagram is that the Gröbner fan is some big complicated structure with lots of vertices and edges. The tropical fan is some less complicated structure, which is a subfan of the Gröbner fan. And what's interesting is that if I pick a positive structure pick the positive part of the Grassmannian, then there's a positive part of the tropical Grassmannian, which in the canonical ordering is just these five vertices connected with a star shape. And it turns out that those 5 rays are sufficient to specify a single maximal cone in the Gröbner fan. So if I pick a positivity structure on the Grassmannian, there's a canonical Gröbner cone in the Gröbner fan. So therefore, there's a canonical Gröbner basis given by the positivity structure and a canonical initial ideal. And that initial ideal that you get is just the set of these things in the middle of these relations where you have crossing labels. I don't know if that's obvious, it's a crossing, but I've got 1, 3, 2, 4. So 3 is between 2 and 4. So 1, 3 crosses 2, 4. Okay, so we get a canonical Gröbner cone with, sorry? Yes, sorry. Whose initial ideal is given by the set. In this case, it's just the set of all exchange monomials of the cluster algebra. Okay, so it's like A prime pairs where A prime is the mutation of A. It's the set of all AA prime pairs. So therefore, you can read off from this, all the factors are the letters. And all the list of generators that you have are the list of forbidden singularity pairs in the symbol of the function that you want to study. Okay, so AA prime, that exhausts all the non-neighbors in the cluster algebra. Okay, so then now I did it for GR25, but you can go and study this for GR26, you get the same thing. And GR36, and this is where this paper of Bossinger, Mohammadi, and Nahara Chavez is relevant. They studied GR2n and GR36. And for GR2n, it's literally, as I said, for GR36, to see the same phenomenon, you actually have to extend the ideal by some suitable choice of extra variables. And those variables are just the quadratic letters from the cluster algebra. So you have to introduce some new coordinates into your ideal. Once you've done that, the rays of the positive tropical Grassmannian define a unique canonical Gröbner cone, whose initial ideal is the list of all non-adjacent letters from the cluster algebra. And we've also gone on and checked the case. It's also the case for GR47, where there's 462 pairs, that AA prime pairs that are generate the initial ideal for the Gröbner cone that's spanned by the positive rays of the tropical Grassmannian. So that's the punchline. It's, you can recover the same combinatorics and the same list of properties that are relevant for these scattering amplitudes, also by just studying the Gröbner fan for the Klucker ideal of the Grassmannian. I'll finish there, thanks.
I think I misunderstood something you said at the end. So you rule out things like in your topic 1, 2, 4, 5, 2, 3, 5, 6.
Yes.
They're just very far apart as it stands. They're not an exchange pair.
They are an exchange pair, right? Yeah, so the question is, why did I rule out? The question is, why did I rule out 1, 2, 4, 5 being next to 2, 3, 5, 6? And these variables label these square faces on this polytope. And they're connected by an edge, which is the exchange relation. So they're one step. In fact, in GR2n, everything is either in the same cluster or one step away. Okay. Absolutely. That's correct. Yes. So no, that's it. So what I wrote as AA prime is a G2 phenomenon, but what you get for GR36, GR37 is all forbidden pairs, not just mutation pairs. Yeah.
We recognize this because you're just looking at the ones where they're not extra points. So you're only allowed sequences where the adjacent guys are. This relationship between adjacent ones just depends on the two letters. In fact, not on whether or not you can find clusters with them in. Because the property you can compute just from the two letters.
Yes. Okay.
It's sort of what you showed, I think.
Okay. All right. I should discuss them. Yeah, yeah.
Yeah. There seems to be a question in the chat from Melissa Sherman-Bennett saying these algebraic symbol letters, are they somewhere in this?
Yes. So it's a slightly different story, but you can recover the algebraic symbol letters. So I drew GR48, so I guess I ought to talk about it. So, so the tropical fan, if you study the tropical fan for GR48, you find, well, there's a subtlety. There are many different choices of tropical fan that you could study. Let me take the simplest one, which is not even to tropicalize all the minors available to you. So it's actually a sub-fan of what we would canonically call the tropical Grassmannian, even in GR48. So if I take some sub-fan of that, you will find, actually it's there's a Z2 invariance of sort of parity operation on this these letters here. So if I can take a sort of maximal subset that's invariant, subset of minors that's invariant under this Z2 operation, I can sketch what they are. You find a fan with 274 rays. 272 of them correspond to G vectors of the cluster algebra and are associated to rationally generated cluster variables. And then there's two other rays that are not G vectors, but are limits of infinite sequences of G vectors in some suitable identified affine double arrow subalgebra. You keep mutating on alternate nodes, and you get an infinite sequence of G vectors that asymptote to some new direction. And those are rays of the tropical Grassmannian. So if you study the sequences of G vectors that asymptote to these new rays, and you compute what are the cluster variables as you do this mutation, you get something like a Fibonacci type recurrence relation. It's a priori, it's second order, but you can show that it's equivalent to a first order recurrence relation. And then from the generating function for the sequence of cluster variables, you can read off for each sequence, you can read off an algebraic letter, which contains the square roots. So you get by choosing these sequences, you get precisely the, I think, 18 algebraic letters that Anastasia was referring to in her previous talk. Now, how that will show up in this story related to the Gröbner basis is another question that I haven't studied yet. You'd have to start refining or introducing more and more variables, presumably, to try and understand the structure of this initial ideal. And maybe in that sequence of operations, you can recover also these square root variables.
Very good topic for future discussion. I think if it's okay, we should